So there are a couple of theorems which I don't want to prove by myself at this course because we have no time for it, but these theorems are very, very important. So there are some specific tools to prove properties of characteristic classes, and one of them is splitting principle. What does it mean? Assume we have a vector bundle. It can be real or complex, doesn't matter. The statement is as follows. There exists another space B1 and a map from B1 to B. If you deal with a smooth category, B1 will be manifold and F will be smooth. If you deal with topological spaces, it can be just topological space. But since we're working only with manifolds, so B1 is manifold, F is smooth map. Such that if you take a pullback of this vector bundle to B1, this new vector bundle has very specific property. First of all, pullback of this vector bundle to B1 is the Whitney sum of line bundles. So our vector bundle was of rank n, or of dimension n. The trick is to take a pullback over very specific space B1 such that pullback is just Whitney sum of line bundles. And the second statement is very important, that if you look at the mapping cohomology, you will see that you map cohomology of B to cohomology of B1. In our case, and it is general statement, so it doesn't matter which cohomology theory you use here, but in our case, we speak about the RAM cohomology, because we speak in differential form, so I write the RAM cohomology. This map is monomorphism. What does it mean? It means exactly the following statement. If you have some specific relation between characteristic classes of the vector bundle E, you will see the same relation here, because this guy is a monomorphism. But to check this relation, you can check it not for the vector bundle over B, but for vector bundle over B1. And this vector bundle is much more simpler, just sum of line bundles. And characteristic classes of line bundles, C1, so total Chern class of L. So if we speak about complex vector bundles, so what is C1? It's very simple. 1 plus C1 of L and nothing more. It's very simple. So then you speak about characteristic classes of L1 plus Ln. You just consider product of and you obtain elementary symmetric polynomials. It's very, very simple. So it's not. So this is a very important tool for proving some properties of characteristic classes and checking some identities. So this is a very nice theorem. Unfortunately, I skip the proof. And another statement is about universal characteristic classes. So we already know that invariance of unitary group, invariant polynomials on this Lie algebra with respect to its Lie group. What are the formula? What is the algebra of invariance in this case? Let me know. Chern classes, yes? The polynomials of these guys. Okay, what we can say about invariance for orthogonal group? Hmm? Yes, but up to which dimension? Pantragen is correct, but up to which dimension? So you divide n by 2 and take integer part. And what happens if you take this invariance for a special orthogonal algebra? As Lie algebra, they are the same, but you consider add invariance with respect to different Lie groups. This is group a little bit bigger than this one, so these two algebras are different. The answer is follows. It is the same P1, Pk if n is equal to k plus 1. And it is a little bit trickier than n is even, because it's algebra of polynomials on these Pantragen classes, and in even dimension you have Pfaffian, which gives you Euler class. So n is equal to 2k, and you still have Pantragen class with number k, but it is e squared. So you can do two things. You can add Pantragen class here, but you need to impose this relation. Otherwise, you can write polynomial ring on these generators, but you should remember that pk is e squared. Okay, there is another point of view to this thing. Classification of vector bundles up to isomorphism. There is so-called Grassmannian. Oh, so let me start from dimension 1. What I can say about line bundles. And for every line bundle over space B, there exists a map F from B to projective space, infinite dimensional projective space. It works for both cases, real and complex, such that over projective space you have a tautological line bundle. There exists a map such that L is just pullback of this gamma. But this is a not classification theorem, it's just a statement. Classification theorem would be a little bit different. What happens if you change F by homotopy? The map F is not unique, it just exists. There is a one-to-one relation between isomorphism classes these are homotopic classes of continuous maps. So every line bundle is classified by homotopy class of some map from B to P infinity. And on the other hand, if you have two homotopy maps here, then you will obtain two isomorphic line bundles. Well, and it's a very simple case of classification theorem. So now I will give you general type. There are 3 types of classification theorem. For C bundles or, UN bundles to be accurate. These are real bundles and these are real and oriented bundles. Then in these 3 cases we have specific space. In this case we have complex Grassmannian, which I denote by Grassmannian over complex numbers, and now I write 2 indices. One index is infinity and another one is n. So what does it mean? It is Grassmannian of n-dimensional planes in infinite-dimensional vector space. But people usually write it in this form. Direct limit of complex Grassmannians of Kn. So you take finite-dimensional vector space of dimension k. Inside that you consider k-dimensional planes, and the space of these planes is Grassmannian. The definition is similar to definition of projective space. Then you take direct limit over k. This guy is Grassmannian. Is it okay? I believe that most people in this room know what is a Grassmannian and why it classifies vector bundles. So in this case we consider real Grassmannian. Again, it's n-dimensional planes in blah blah blah. Those who are in complex space, these are in real space. Make a guess, please, make a guess. What happens to this vector bundles? Special orthogonal group. We need to give another definition of Grassmannian.
Grassmannian of oriented planes.
Sure. You consider each plane comes with 2 orientations. So we write here Grassmannian, real Grassmannian of infinite of planes of dimension n, but each plane is considered with orientation. It is complex Grassmannian, doesn't need to write something about orientation. This is unoriented, this one is oriented. So in each case, isomorphism classes of vector bundles. What is multi-dot? It is one of these structure groups. So you consider isomorphism classes of vector bundles with one of these 3 structure groups. Over B. Yes. Are in one-to-one correspondence with homotopy classes from B to corresponding Grassmannian. For each case, you have corresponding Grassmannian. So you write this. This map is just taking pullback. So if you have a map from B to Grassmannian, you can construct a vector bundle. Construction from this, from the vector bundle to Grassmannian is a little bit tricky. A question to those guys who sit from the row 2nd to the infinity. Where is a mistake in my definition? In this statement, there is a mistake. I think there is a mistake. Base B should be compact. Otherwise, you will not be able to map from here to there. So, this point of view, so identification of isomorphism classes with maps to Grassmannian is very nice way to think about characteristic classes from categorical point of view. So here we defined characteristic classes using Chern-Weil construction. Yes? So we We take connection, we take its curvature, we substitute curvatures to some polynomial, then we obtain characteristic class. But we can construct a characteristic class as a... So what is a characteristic class in general? In from very general point of view, in very general setting. We already discussed it, but let us repeat it. So Chern class in very general, char class, not Chern, characteristic class. In very general setting is as follows. So if you have a vector bundle over base B, you have a map from vector bundles to, it's a rule which gives you a class and cohomology of B for each vector bundle. But you need this map to be natural. In the following sense, if you take a pullback of the vector bundle E and calculate its characteristic class, this should coincide with pullback of characteristic class for vector bundle Xi. And it means that all characteristic classes are defined by value of C of tautological bundle over Grassmannian. Any C is defined by its value on tautological bundle over corresponding Grassmannian. Indeed, each vector space or each vector bundle is a pullback of tautological bundle over Grassmannian with respect to some map. So if you know characteristic classes of Grassmannian or of tautological bundle over Grassmannian, then you can say you can construct any characteristic class, no problem. The question, how to calculate cohomology of Grassmannian? Because each cohomology class in Grassmannian provides you by this formula characteristic class of any vector bundle. We are very lucky because even in this general setting we can prove, we will not prove this statement, but it's not very difficult, but it requires some tools from algebraic topology, that's why we skip it. So, cohomology of complex Grassmannian. Again, we work in the RAM cohomology, that's why I write here the RAM. So we take complex Grassmannian of n-dimensional planes in infinite dimensional space, and we are lucky that we have such an isomorphism. That means that Chern-Weil construction gives you all characteristic classes which can be obtained from algebraic topology approach of this type. Same happens here. If you take cohomology of real Grassmannian, you will obtain this formula. And if you calculate the RAM cohomology of oriented Grassmannian, okay, I skip the proof, but the statement, roughly speaking, is as follows. If you have another approach to characteristic classes which comes from algebraic topology, you will obtain exactly the same characteristic classes as in Chern-Weil approach. The only difference is if you look for coefficients which are not real cohomology. So you can imagine that you calculated integer valued cohomology, not the RAM, but instead of this you will write here integer numbers. Yes, then the statement still holds. This is this cohomology with integer coefficients gives you the same Chern classes, but with values and integer cohomology. More or less the same comes from for Pantragen classes, but you need to ignore torsion here because cohomology of Grassmannian contains torsion of order 2. You need to ignore it. Okay, so I think it's enough for general picture, but I have a bunch of problems. And I will fix them here. So I think that we can discuss them on Friday, just to finish our discussion of characteristic classes. So exercises. In any way they go for examination. So assume we have xi, which is a real bundle. Then you can calculate its K Pantragen class. At the same time, you can consider its complexification and calculate its Chern class with number C to K. This will be minus 1 to the power of K.
So what do we need to do?
So we need to check. So imagine you have vector bundle. You can equip it with a connection. You can calculate its curvature form. Then you substitute it to elementary symmetric polynomials. Yes, and you calculate Pantragen class. But you can do another thing. You can take vector bundle, complexify it. So it means that instead of real vector spaces and fibers, you substitute complex vector spaces. So you have complexification of vector bundle. Then you can calculate its Chern class. This guy is of dimension 4k, this guy is also of dimension 4k. And they are the same up to this sign. Clear? Exercise number 2. Xi is a real vector bundle. We obviously skip here EE odd dimensional Chern classes. What can be said about these classes? Maybe these are some new characteristic classes of very tricky nature. Okay? Maybe. You check it. If these will be new characteristic classes for real vector bundles, you will obtain Fields medal, I claim. So, if Xi is a C vector bundle, complex vector bundle, and of rank R, complex rank is equal to R, then you can calculate its Chern class of top dimension. Sorry, I write different letters for same object. So Xi is a vector bundle, complex vector bundle of rank R. It means that fibers are R-dimensional complex vector spaces. You can calculate it, calculate Chern class with number R, top dimension Chern class. There are no Chern classes with dimension greater than R. And also you can calculate Euler class of its so how to write it? So you forget about complex structure. You obtain just real vector bundle. Of which dimension? Any complex space of dimension R is vector space over reals of dimension 2R, because you have one axis along real line and another axis along imaginary line. So this guy is of dimension rank of over R of this vector bundle is 2R. So we have two classes, Chern class and Euler class. Check that they are the same. They are given by different differential form maybe, but you should check that they are the same. Cool. Exercise number 4. So if you have Xi is a real vector bundle, then you can do the following. You can take tot genus of its complexification and you can calculate a hat genus of psi itself. My statement is that they are almost the same, but a little bit different. This guy is square of this one. I think that we can calculate also Euler class of psi plus eta, and to check that is. So if you have two oriented vector bundles, real vector bundles psi and eta, you can take its Whitney sum, it's still oriented, you can calculate its Euler class, and this is a formula. I think it's enough for Friday, because I also have a couple of exercises. Oh, no, I have yet one more. I have one more. Okay, let me write one more exercise. This will be given in very unclear way. So let me remind you that when we speak about Chern classes, there is a so-called axiomatic description. First, CK are natural. Then we have Whitney sum. And relation between total Chern classes of these three bundles. So if you calculate total Chern class of these two vector bundles and multiply them, you will obtain Chern class of Whitney sum, total Chern class. Well, were there some other axioms? There was the axiom of dimension, yes, so C0 is 1, yes, and Cn is of psi is 0 for n greater than rank of psi, yes? It's a kind of normalization. This is normalization. Since every vector bundle is a pullback of a vector it splits to line, to Whitney sum of line bundles, so everything is defined by Chern classes of line bundles. Line bundle is a pullback of a line bundle over Cp n, Cp infinity, and the normalization is about value of C1 for gamma over Cp1. It is enough to calculate what happens. Because if you know that this guy is non-zero, then you obtain non-zero for tautological line bundle over Cp infinity. The only thing you need to check that is value of first Chern class for this tautological line bundle. It's a very, very simple thing. What is my unclear statement? Let us embed, so Cp1 is, what is Cp1? S2. Yes. But with very specific orientation, because Cp1 is a complex manifold. It comes equipped with orientation. So imagine you have tautological line bundle over Cp1, and I want to embed it to Cp1 cross C2 into trivial one. It's obviously embedded because gamma consists of vectors which belong to a line which represents point here. So it's naturally to think that gamma sits here. The connection here is just projection. It's just taking derivative, then projecting. So you have a section of gamma, it sits here, you take a derivative, you obtain section of this bundle, but not of gamma. And then you make a projection, orthogonal projection, as we already did for real case. First, calculate A, connection form. The question, A is U1 valued. If yes, calculate integral of C1 of gamma over S2. This will be normalization. Because, let me repeat. So we take tautological line bundle over CP1. We embed it into trivial bundle. Then we do the following. This vector bundle has connection. Just take in derivative, no A. You don't need a connection form if you have trivial bundle. Among connections here, we can take just trivial connection, taking just derivatives. But to define connection on subbundle, we take projection into fibers, orthogonal projection. Okay. In this way, we obtain connection on gamma. The problem is, exercise is calculate one forms of connection for this nabla. It could happen that connection form will not be U1 valued. It could happen. Nobody knows. You check. If not, then you stop. You say this approach doesn't work. But if it is U1 valued, then you calculate, then you can define C1 of gamma, and then you calculate this integral. And then you will know, oh, not S2, CP1. Then you will obtain the normalization axiom. You will know the value C1 of tautological line bundle, which belongs to cohomology of dimension 2 of CP1. These are reals. The problem is that you can take any value of this guy to obtain theory of characteristic classes. Why not? Every value of C1 here gives you theory of characteristic classes. You can, for example, take it equal to 0. Then nothing happens. But nobody wants to deal with trivial things, so you need to check a generator here. Well, but there is an algebraic topology approach here. Then you take things with values in integers. So roughly speaking, you need to choose between 1 and -1. Because in this group, you have two generators, 1 and -1. If it were integers, you will take two generators, 1 and -1. Then you calculate this thing, and you will know the answer, what to choose. And this explains you the multiple I over 2 pi, something like that. So you know that then when we substituted curvature into invariant polynomials, there were something like these guys. So, on Friday, we will know the truth. I hope so. Okay, so now characteristic classes are over. We know everything. Now let's speak about differential operators. So, we will speak about partial derivative operations, and we will write for them the following abbreviation, PDO. It is subset of much more general theory of pseudo-differential operators. We will not speak about pseudo-differential operators for this following. We have no time for it. For us, this is enough. And let me repeat that inside this guy, we have operators which are called Dirac type operators. And our index theorem will be about operators of this very specific form. In every applications which you know, the operators are of Dirac type. So that's why it is enough for us. Okay, so what we're speaking about. Imagine that we have two vector bundles, E1 and E2 over the same smooth manifold M. And we want to consider smooth sections of one and another. And obviously there are maps from one to another. So let me write here L. What can you say about linearity about this map? Imagine it is differential operator. We don't know the definition, but imagine that this is a differential operator. What can you say about linearity of this procedure? So we speak about operators from E1 to E2. Total collection of it is a set of maps from sections. I will not write infinity here sometimes. So I said, well, from time to time I will forget about infinity. So L is C linear. Oh, sorry, YC is just R linear. Okay, just R linear. Wait a moment. Wait a moment. Maybe it's better to write that these are complex vector bundles. This is C linear. Well, no statement about linearity over functions. Well, inside this guy we have partial derivative operators which are C linear. So inside of this guy we have PDO of 0. These are operators. L is C infinity of M linear. Actually, it is a section. We discussed it earlier. It is sections of very simple bundle. A bundle of such type. You take E1 star dual in tensor product with E2. And this is just smooth sections of this bundle, so-called home from E1 to E2. Okay. And now we want to define operators of some order with very, very simple inductive construction. Let me define for F and L linear operator, which is defined, I will define it in this way: add F on L, or sometimes I will write add F L. It is just commutator of L with F. To be more precise, it still belongs to op from E1 to E2, but it is a way, in some sense, this operation lowers the order of L. I will write you a formula and examples, and you will see why this happens. So how this guy operates on sections. So we apply this operator, which should be defined, to a section S. And by definition, this is L applied to section times F minus L of S times F. Could you explain me why we think that the order of this expression should be lower than the order of L itself? It's quite simple. You apply, imagine that L is a differential operator. Then you, which you know, this is a very general setting, but imagine that L is a differential operator that you already know, some partial derivative. Then you take derivative of this expression, you have Leibniz formula. in which some derivatives are applied to f and some derivatives are applied to s. The summand where you apply all derivatives to s is cancelled by this summand. Yes, so in this expression, number of derivatives applied to section S is strictly lower than the order of L itself here. So let me finish the definition. So we say partial derivative operators of order m plus 1 from E1 to E2 are defined inductively by the following way. These are L here. So linear map, which is linears over scalars, constant functions, such that for any smooth function, this operation is an operator of order smaller than m plus 1, PDO m. This is an inductive definition of order. The tricky part is as follows. I don't want to write the formula for the operator in coordinates. That's why I take this coordinate-free approach. Okay, now we be careful here. So L belongs to PDO m minus PDO m minus 1, then we say that the order of L is equal to m. It means that it contains derivatives of order m, but not only m minus 1. But if we have, and we denote this space by PDO m without brackets. And if L belongs to PDO m, then we say that order of L is not greater than m. And now we consider some examples. Operators of zero order are just linear maps from one vector bundle to another. Okay, let us consider very simple example. So assume we have one-dimensional complex vector bundle over manifold M. Then its smooth sections, of this guy can be identified with smooth functions on M. Because what is a section? You say that at this point, at some point, you assign a number on the line. So that's just smooth function. Let L be partial derivative along some local coordinate, di. Yes, to be honest, it happens not on, the formula is working not on M itself, but only in one chart. Okay, let us write here chart. An open set in Euclidean space. The question, which it is a differential operator? I believe so, because we see the derivative. What can be said about my claim is di belongs to PDO 1 from 1 to 1. Okay, in case then the same vector bundle appears in both sides, in both arguments, we will write only one letter. So, and we write PDO of EE. This will be PDO just E. Yes, and okay, let us introduce notation. Then we write PDO, we mean the union of all PDO M's. So collection of all operators of such type. So my claim is that this guy is a differential operator of order 1. partial differential operator. Okay, let's check. Take a smooth function, calculate add f of di, and we apply it to section S. Let's check. What should we do? We should apply this formula. We take partial derivative of the product f by s. Okay, in this formula they are not the same. This is a section, this is a function in general. But since we deal with trivial one-dimensional vector bundle, these guys are both smooth functions. F di of s. Very complicated formula, but we can calculate it mentally. Don't need to write it. This is di of f times s. Everything else cancels. The question, so what is written here? We take a section and we multiply it by a function. It's linear operator over functions. So this map belongs to PDO 0. It's C infinity M linear map. So this is PDO of f. From this it follows that di is partial derivative operator of order 1. It's not a derivative operator of order 0. It's not linear over functions. So which is PDO 1 minus PDO 0. Okay, very good. Second example. Let me give you this statement as an exercise, because I want to use it now. If you take a composition of two partial derivative operators of two different orders, okay, it's not correct. Let me write it in this way. So we have operator L, which belongs PDO M, which goes from E1 to E2, and operator L tilde, which belongs PDO of order N, ML, okay, L, K, from E2 to E3. Then I can consider a composition of them. Tell me, please, in which order? In which order these two operators can be composed?
First L, then L tilde.
Yes. L tilde, composition with L, belongs to partial derivative operator of order which is a sum of these two orders. From sections of E1 to sections of E3. So this is an exercise to check it using my formal definition. Well, in some intuitive picture it's obvious, because this operator contains monomials with at most m differential operators taking partial derivatives, yes? And here at most k. Then you take a composition, you can, obviously the number of differential of partial derivatives will be not greater than this number. We have a very interesting, what can be said about connection? Can we consider connection as a partial derivative operator or not? First of all, connection works from sections of one vector bundle to sections of some other vector bundle. Please remind me. Sorry? Cotangent, yes, that's correct. T star of M tensor with E. So this is a source, this is a target. Now we try to, we wrote that this guy is not linear over functions. It's obvious. So nabla is not linear over C infinity of M, hence does not belong to PDO of zero order. But let us check what happens, what happen if we consider this thing applied to a section S. What we can write here, what we should write. So we consider nabla of Fs. So here we have product of two different objects. S is a section, F is a smooth function. No problem. Again, nabla S is a section, F is a function. Well, but in the axiom of F, of nabla, there was a formula which gives us possibility to rewrite it by a kind of Leibniz formula. And we obtain df tensor with nabla S. Is it okay? Yes, sure, it's incorrect. Because in each summand, you have only one derivative, either exterior derivative or nabla. So correct formula is this one. This is a linear operator. This is linear operator. So this guy belongs to PDO 0, hence nabla. This guy is PDO of order 1. Exactly order 1 because it's not of zero order, so it's PDO 1. Well, we have another differential operator. Exterior derivative. Let us calculate what happens to what we can say about exterior derivative, d, which works from k forms on M to k plus 1 forms on M. First of all, I need to rewrite these guys as the sections of some bundle. It's just space. That's my discussion was about sections of bundles. How to consider differential forms of sections? Tell me, please.
Exterior.
Yes, actually, it's sections of k exterior power of cotangent bundle. This is sections on lambda k plus 1 of cotangent bundle. That's derivative. Okay, now I need to understand what does it mean. What this thing is doing with a section. Section is a differential form. Okay, let us apply this guy to differential form omega. By definition, it is just derivative of what? Function f multiplied by differential form. Just differential form can be multiplied by function. I did it. Minus function multiplied by differential of omega. Difficult. What is the value of this? Yeah. And what about sine? Sine is correct. So df wedge omega, so it's linear map now, because it sends omega to something which linearly depends on omega, linearly over Cm. So this operation is PDO 0. Hence, exterior derivative is PDO of first order, which goes from this vector bundle to this vector bundle. Do you know some other differential operators? Дальбо. Okay, it will be. We will discuss it a little bit later.
I don't remember exactly. It's called contraction.
Where contraction?
Which decreases power. Which decreases population.
Conjugate one. Formally adjoint.
No, take a value at a vector.
Contraction. But I guess it does not contain derivatives. Okay, let us. So that's a cool thing. Okay, let us discuss it. We have a map, which is contraction. It means the following: we have a vector field xi. Xi is a vector field, and then sends differential form of order k to differential form of k minus 1 of m, and it works as follows. It sends form omega, because omega is skew-symmetric function on vector fields. Yes. It sends omega to new object I xi of omega, and it is calculated in the following way. So you calculate it on the vector fields with numbers from 1 to k minus 1, because this object is differential form of degree k minus 1. And its value is given by the following. It depends on your preferences. I put xi on the first place. Somebody puts xi on the last place. And you substitute these arguments to other places, so now you calculated omega from k arguments. So this is a map from differential forms of order k to differential forms of order k minus 1. And the question is, what is the order of this operator? I guess it's 0, because you can multiply omega by function, and the result also will be multiplied by function. So this guy is very good example of partial derivative operator, which has no derivatives. It's linear, 0 order. Very good. The reason why we can consider differential operators locally is as follows. Partial derivative operators are local. I will explain you what does it mean. Assume we have a section, and we have L of S. So this is a section of vector bundle E. L of S is a section of first, it is a section of a second. You have two sections, and they have supports. Which support is greater? Statement. So there's a closure of the points where the section S is non-zero. And here is a closure of the points there L of S is not 0. Which support is greater? Or maybe they have no relation one to another. Make a guess. Make a guess.
Looks like the first one should be bigger.
The first one should be bigger for what reason?
Well, if you take, say, partial derivative of a function which is already 0 in the neighborhood, then you take it 0.
Yes. The idea is follows. So you have places where function is 0, places where function changes, section, 0 section, it changes, then it's constant, then it again changes, and then it goes to 0. So this is a section S. Where is the support of this section? Here. Yes, there's a place where it's not 0. What can we say about derivatives of section? Say d1 of S, how it behaves. Look here, here it's 0. Here it's constant. Again 0, constant. So we have 0, it goes up and stabilize. Well, how to write it? Derivative. Well, okay. I guess the support of the derivative of this section looks like this. and support is smaller. So the statement is that then you apply derivative operators, then support cannot be bigger than initial support. Okay, how to prove it? Proof. Consider for any U open set such that U contains support of the section. There exists a function with the properties. F is identically 1 on support of S. F is identically 0 on M outside U. And it changes from 1 to 0 on U. So what does it mean? So it's a kind of bump function. So we have support, it's closed subset. Then I take a little bit bigger open set and then consider function which is doing the following. Here it is 0, here it is 1, and here it cuts. So this cut can be done arbitrarily small, because this function exists for any open set which contains support. So you can imagine that this gap is sufficiently small. But we do not use this no sufficiently small. We just consider the case that U is any open set. It is enough for us. What I want to check? I want to check what I can say about so let us consider this product, F times S. Tell me, please, what is support of this product? Support of S, the same. So now, well, but I guess that F and Fs and S are the same. What do you think about it? S is not 0 here. Here F is equal to 1. That's why if you multiply the section S by function F, you still obtain section S. Now we calculate how we do it. Okay, sorry, I forget to do one thing. By induction on the order of L. Induction on the order of L. For L of order 0, it is obvious. Because if our operator is just linear map over functions, then obviously support is the same. Okay, how to rewrite it? Let us subtract here what I want to subtract. F ls, and then I obviously should add it back. So I just subtract this guy and edit it again. Tell me, please, this thing under this bracket, what is it? Yes, this guy is add f, applied to L, and then applied to S. This thing has order smaller than order of L. So by induction hypothesis, the support of this guy is smaller than support of S. By induction hypothesis, its support is contained in support of section S. Well, and what can you tell me about the support of this object? No, I would say that it is U with bar. It's closure of U. Because F, generally speaking, F can be non-zero on U. So it is. Okay, so in general, support is not greater than U. And since U is arbitrary open set which contains that guy, so we can write, so support of L of S is contained in intersection of all U, of such U's. So it is support of S. That's all. Roughly speaking, it means that value of L of S depends on behavior of, so let me repeat, the value of this guy is defined by value of S in arbitrary small neighborhood of the point you consider. That means local. Maybe you can say that it depends on the S, its derivatives, its second derivatives, blah, blah, blah. So if you have two sections which coincide in the small neighborhood of the point, then their L of S will be the same. Okay. Now we pass to very important ingredient of our study, so-called symbol. Are you familiar with symbol?
Well,
Hmm?
question. From
Yeah.
this locality, a question arises if these partial derivative operators form a sheaf or something.
Sorry? We consider one partial derivative operator.
Yes, but all of them, do they form, as they can be defined locally, then there are ways of gluing them, or?
Oh, well, the next question, can we glue them together?
Or do they
Yes,
in
again.
any way form a sheaf, or?
No, be careful with that. So it means that I guess that this guy is defined on a sheaf of sections of some.
But themselves?
I do not think so, because imagine you have a. Maybe yes, but you need to carefully explain every detail. Because I thought about the following example. I think that you have a connection. You can define connection locally in each chart. You say that they are compatible if there is some rule to recalculate curvature forms from one coordinate to another. And on triple intersection, you have gluing cocycle conditions. So you have pre-sheaf axiom, no problem. And I think that sheaf axiom is also okay. So patching differential operator from local data, I guess it's okay. Okay, let's speak about symbol. Are you familiar with the name of symbol in differential equations? Have you ever met this?
Yes. It was on the course of differential equations.
Well, and what does it mean?
It's a polynomial to which we insert derivatives and get.
Yes, correct. And local coordinates. Imagine we have some differential operator. Oh well, so not good. So we have function multiplied d by dx, function d dx squared, and it's enough. So this is a differential operator. Okay. It has symbol. What does it mean? You insert here, instead of derivative, you insert here new variable. In physics, it's momenta. In differential geometry, it will be cotangent vector. So in local charts, it will look like this. Instead of looking for differential operator, you put here some new variable. So if you have different variables, then you need to write different xi's. One xi is for x, another one for y. Well, but I want to define symbol in a coordinate-free approach, so let me do the following a kind of exercise. M, L belongs to partial derivative operators of order M. And let functions f1, etc., fm be functions be smooth functions. Then I want to consider this expression. What do you think about this operator? It works on sections of E1 and E2. So it should be, because we defined order by induction, so it should be differential operator of some order. Guess of which order? Zero. Because I took exactly the same number of functions. So this guy is just C infinity linear map from sections of this guy to sections of this guy. What I want to check? I want to check statement. Statement. It is symmetric in F1, etc., Fm. For simplicity, I need to check what happens if I consider this expression and this expression. Just to check that I can interchange the order of two neighboring f's. Let's check it. How it works? So it works as this. So first of all, I calculate the guy which sits inside here. Oh well, that's a problem. We need to apply it to the section. The question, very interesting question, in which order I calculate the action of add on operators, starting from F or starting from G? So I should write here one commutator, then to expand another commutator. Which is the first commutator?
I think it's this thing in brackets add G applied to Fs. Add GL applied.
Yes, this thing is inside. We cannot see it. Then, so that means that first of all we expand this expression starting from F. So we write here add of g applied to L, apply it to Fs, and then we subtract this thing, add g L applied to S. Okay, expand it further. So what is written here? L of g times f gs minus g outside L of fs. No problem. What is written here? Minus f. Then we write L of g of s plus what? G outside is it okay? Not at all. Everything crashed. Nothing works. Or I'm not right. Well, what I want to prove?
Why doesn't it work? It looks.
I forget that I want to prove.
It looks that this thing is symmetric on f and g. So
Yeah, so everything is okay. So if I interchange here f and g, then I interchange f and g here, and nothing happens.
yes.
Well, so very good. So if we start from this guy, this gives you exactly the same answer. So very good. Okay. This guy is symmetric in f and g. So that's why I don't want to write this thing. So I want to write as a multi-argument object. It's possible. Very good. Symmetric, well, obviously it is multilinear in F. I forget to write it. Multilinear in F. Well, I think my time is more or less over. So let me finish with so-called Hadamard lemma. So let us prove something very simple in the end, and we start next lecture from discussion what a symbol is. Because after definition of symbol, I need to give you a bunch of examples. Without examples, it doesn't work. So let us finish with Hadamard lemma, which is a kind of Taylor expansion. But I like it. A smooth function S function f admits a representation f of x is equal to f of x0 plus sum of x k minus x k0, sum over k, and here we have functions hk of x. So what is written here? The value at the point x0. This is a linear part of Taylor expansion, and plus some residue, yes? Other terms which are hidden here, such that hk at the point x0 is the same as partial derivative over function k at point x0. The proof is in one line. How to check it? We write the following formula. We write I want to apply a Newton-Leibniz formula. To what? So in the space, I consider a segment starting from point x0 and which goes to point x. So this is an integral from 0 to 1 over dt. And what should I integrate? Okay, this is a function which I want. I take a derivative of this function in some kind of clever way. So because I need to parameterize the segment by parameter t from 0 to 1. So we start from the point x0, then we take linear parameter, and if t is equal to 0, we are in the point x0, but then I arrive to t equal to 1, I should obtain point x. So there is no other way as to write it in this form. Yes, but it's not correct. What should I change here? Derivative, yes, I should take derivative here by t. Okay, guys, I guess you can calculate the derivative mentally. You don't need to. It's complicated. It's composition. Yes, it's function of many arguments, and on each coordinate you have such an expression. So actually, what you are integrating? You are integrating the expression xk minus xk0. This derivative of this expression times dk of f of x0 plus t x minus x0. So this is linear part which does not depend on t, it goes outside. So the hk is just integral from 0 to 1 of what? Of dt of dk of f, blah, 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 blah. So, and everything now is clear. If you are very good at calculus, you can say me that my Hadamard lemma is stated in not so correct way, because I need to say the function f is sufficiently smooth, and the neighborhood of point x0 where f is defined should be star shape. Otherwise, I cannot consider segment. Star shaped of x0. After that, I claim the following. I believe that here we have some guys who like algebraic geometry. Consider ideal of smooth functions with 0 at point P0 from our manifold. Why it is an ideal? Obviously, if you multiply function which has 0 at this point by some other function, you still obtain function which has 0 at this point. And also it is space closed under addition and multiplying by a scalar. Very good. It is an ideal. Next question. What in algebra we denote by square of ideal? It's a very difficult thing. What is a square of ideal?
Or possible products.
It's not enough. Yes. Yes. You need to take finite sums of these guys where fk and jk belongs to the ideal. Because if you have something which is a product of two such functions and you take a sum of them, this could be not presentable in this form. So that's why you need to take linear combinations. Very good. So this is a square of ideal. The claim is that if you take a quotient, which one is biggest? Okay, which space is bigger? This one smaller. This one bigger. Because these functions obviously vanish at point P0. So contains square of this ideal, and you can take a quotient of. So this is a final statement. Tell me, please, what can be said about this quotient? From what it consists?
Linear terms.
Linear terms.
Linear terms, yes. Linear terms can be of two natures. It can be covector or can be vector.
Those are
Covectors. Because if you look at the Hadamard lemma, you will see that this construction recovers value of hk's at point P0. So it's just derivatives. So this is a cotangent space at the point P0 of M. Next time we will use it to, so this isomorphism gives us possibility to take by hands covector using functions. So instead of writing covector, we can consider function which vanishes at the point P0, but you need to think that you can consider function up to addition some other functions of such form. So this is a way to get rid of covector and use functions. And we use this approach to define symbol on the next week. Well, thank you very much.
Thank you.